So cycloaddition reactions, of which Dies Alder is one, involves a pericyclic where two different pi bond containing molecules react to form a cyclic compound. Each reactant loses a pi bond, and the resulting cyclic product has two new sigma bonds. So there is at least a reduction in the degree of on-site aeration. The Dies Alder reaction itself is a thermal 4pi 2pi. In contrast, the 2pi 2pi is photochemical. We'll be focused on the 4pi 2pi. 2pi, which is this Dies Alder reaction, is between a 1,3-diene, which has 4 pi electrons, with a diene lava, a dienophile, which has 2 pi electrons. This generates via a pericyclic reaction a cyclohexene ring. If it's not a cyclohexene ring, it's not Dies Alder. This 4pi 2pi cycloaddition is a thermal event. So we have this triangle to say, yes, it is thermal. We'll be covering the thermodynamics, the kinetics, and the stereospecificity involved in this reaction. We'll also look at some retrosynthesis and molecular orbital treatise towards that Dies Alder. So when we look at the thermodynamics, we see that most Dies Alder reactions are favored at low and moderate temperatures. And the answer is present in this diagram, because you should note that we start off like materials, and you can see that literally we lose energy getting to this product. Why? Because this is enthalpic driven, i.e. because we've lost pi bonds, which are higher in energy than the sigma bonds that we gained. Driven, exothermic, then of course the free energy is negative, i.e. spontaneous. However, at higher temperatures, what's called a retro Dies Alder dominates. Why? Because delta S is negative. Now look closely. We had two molecules to start with, and we generate one. So therefore, with this and the fact that the ring itself has limited rotational forms, we realize delta S being negative. This therefore makes the minus T delta S term positive. So at very high temperatures, then this positive charge will be large. This positive, it's not charge, but this positive value will be large. And so it will dominate. And so delta G would now be positive, i.e. non-spontaneous. But non-spontaneity from left to right means that there is spontaneity from right to left. Hence, the domination of the retro Dies Alder at higher temperatures. There is a stereochemical requirement of Dies Alder, and that is it has to adopt an S-cis conformation. Note, in this diene here, where it's trapped in the S trans, the Dies Alder will not occur. On the other hand, cyclopentadiene, which is trapped in An S-cis conformation is so reactive that it dimerizes at room temperature to give us dicyclopentadiene. One molecule of cyclopentadiene will act as a diene, while the other molecule will act as a dienophile. Of diene and dienophiles are terribly important. Dienophiles with electron withdrawing groups react faster and more efficiently. So herein you can see that the species with the two carbonyls attached to the dienophile is very rapid, and we get stoichiometric yield. The reason for this is that electron withdrawing groups reduces the energy of the LUMO, and so the event occurs more likely. Problem set and ask a simple question: which of the following is most reactive? In the Dies Alder, we could have even asked to give us a ranking system of the reactivity of these fellows. But overall, you can see that the species with the dienophile flanked by two electron withdrawing groups will be the most reactive. Hence, your answer is D. And we have an interesting problem set. So what I want you to do is to pause, work on this problem, and then when you get back, we'll work on this together. Excellent. Now, first you should note that the diene is E, and the dienophile has got both groups on the same side, and so therefore this is Z. So I personally would quickly look at the mechanism, maybe even number our carbons. Draw our ring. And note that on carbon 1 and 2, we have these carbonyls, and they should be syn because we have a Z isomer of the dienophile. So here we have, I'm just going to call these CHO for the aldehyde. On the other hand, on carbon 6, we have a methyl. I'm going to draw this methyl as of the ring. And we should note that we have another methyl which is in the Z position, and that therefore should be opposite, because this is an EZ. And so herein, our answer should be two methyls opposite and two aldehydes on the same side. And so our answer here is B. We should note that we have the two electron withdrawing groups here are on different sides. So why don't we have a think about this and then pause. Once you complete it, we will go through this problem together. Excellent. Note, if the two electron withdrawing groups are on the same side, then we generate this from an alkene that was a E isomer. And so your only answer there should be A. It stands to reason because if you notice, these guys are on the same side. The files are on the same side, and that tells you that the diene itself was an EE. So this here is the EE, and this is, of course, an E, or trans. We're looking at a ring diene reacting with a dienophile. We all have to consider what relationship do the groups, especially the electron withdrawing groups on the dienophile, has on this species bridgehead. And before that, we got to look at the terminology of what exactly is a bridgehead and what exactly is endo and exo to that bridgehead. Well, the exo is a species that is anti to a larger bridgehead. The endo is a species that is syn to the larger bridgehead. So when we look at the Dies Alder, we notice that the electron withdrawing groups are juxtaposed in an endo position, and the exo product is rare. Why? Well, if you look closely at this diagram below, you'll note that there is a favorable pi system interaction between the delta plus of your carbonyl carbon and the electron-rich dienophile. This interaction realizes a click where once the chemical reaction occurs, i.e. the pericyclic, then the position that those groups are in is endo. You could ask a question like this: what is the major product of the following reaction? Now realize that we have a cyclic diene with this dienophile with electron withdrawing groups attached, and so we will create a species with a bridgehead. This is this compound. Note that the nitrile groups are in an endo position. We can also represent this in 2D with the one carbon bridgehead in bold to tell you that it is pointing at the reader, and the nitriles are in hatch, meaning that it is behind the screen. This is a traditional way of indicating the bridgehead, and of course this hatch is telling you that it's behind the screen. So for the retrosynthesis of Dies Alder, we really need to find the diene and dienophile used to create this product. And the first step that we take is to identify the cyclohexene ring, and then we can try to make some sort of disconnect. Now, the disconnect I have here looks like this, and it's quite easy to generate in the sense that all you got to do is draw a reverse product. So you reverse your arrows, and you note you come across a transition state, and this transition state is indicating to you your diene and dienophile. Go ahead and try this one. We'll pause right here. You work on it, and then we'll get back to you and we'll work on it together. Excellent. Now, what diene and dienophile would react to give the product? Now remember, identify the cyclohexene. Once you've found that cyclohexene, then of course you can go ahead and do your disconnect. And that should realize, if you want to, you can always put some arrows in, but that should realize your diene and your dienophile. A molecular orbital treatise of the Dies Alder, we first need to look at molecular orbitals and pericyclic reactions, of which cycloadditions are one. Now, it states here, according to Woodward and Huffman in the 60s, that if the symmetries of both reactants and product orbitals match the reaction, it is said to be symmetry allowed. If the symmetry of the reactants and product orbitals do not correlate, the reaction is symmetry disallowed, i.e. there's no low energy concerted path. And according to Fouquet's approach, then we have to consider only the frontier orbitals, i.e. the HOMO and the LUMO of these species. For a molecular orbital description of cycloaddition, it's quite simple. In a cycloaddition, it involves the donation of electron density from one reactant to another. Not exactly accurate because it's not a heterolytic system, but we should realize that the HOMO of one reactant donates electrons to the LUMO of the other. So in this section, I provide a molecular orbital treatise of the Dies Alder reaction. On the left, notice that we have the molecular orbitals of the 1,3-butadiene. And on the right, we have the molecular orbitals of ethene. Now, in a cycloaddition, and namely this Dies Alder, you realize that the highest occupied molecular orbital is Psi2. You can see that it is a asymmetric molecular orbital, blue-red, red-blue. And the LUMO of the dienophile ethene is also asymmetrical and empty, of course, because it is LUMO. And it got a blue-red, red-blue. So it's also asymmetric. So we got two asymmetric molecular orbitals. And then the click happens. In a cycloaddition, or any pericyclic, bonding can take place only when like phases of both sets of molecular orbitals combine. Now, in the case of the cycloaddition, we have a superficial overlap with asymmetric molecular orbitals. We can also have antiofficial cycloaddition, but this is not the case for us. Herein, you can see with this molecular orbital treatise, we now see why the diene has to adopt an S-cis conformation so that the click can happen. And we also see why we do have this stereochemical outcome because of the superficial addition. We retain this stereochemistry of the diene, and it is reflected in the product. Note, both methyls on the diene adopt a cis position as the dienophile combines with the diene. Herein, you can see the 2E4Z combination to form the trans species. Hope you enjoyed that lecture. I hope it helps you a lot with your work moving forward. Please like and subscribe. There'll be more content to help you on your journey then. Bye for now.